In this section, we'll learn about how carboxylic acids can be chemically reacted to become a new functional group called the ester functional group. Carboxylic acids can undergo many different chemical reactions. In particular, we've already studied the chemical reaction between carboxylic acids and strong bases such as sodium hydroxide. Now we'll see that carboxylic acids can also react with other organic molecules. In one of these reactions, carboxylic acids react with another molecule to form what's called an ester. This is called an ester formation reaction, or more commonly it's referred to as esterification. Esterification is a reaction that involves two different organic molecules. One is a carboxylic acid. We know the structure of a carboxylic acid consists of a carbonyl bond that also is connected to an OH group on one side and an R group or a hydrogen on the other side. This is a carboxylic acid. The other molecule that's necessary for an esterification reaction to take place is an alcohol. An alcohol consists of an OH group directly bonded to a carbon, but it's different from a carboxylic acid because there's no carbonyl bond present. I'll represent this alcohol group in red so that we can keep track of it through the course of this reaction. In an esterification reaction, the carboxylic acid and the alcohol will come together and, provided that an acid catalyst is present, will form a new functional group called an ester. Part of the functional group comes from the skeleton of the carboxylic acid and the other part comes from the alcohol. The part from the carboxylic acid consists of the carbonyl bond as well as the R group or hydrogen that was attached to it. The OH group, however, is removed from the molecule. It's actually essentially removed through a dehydration step because the other thing that gets removed from these two molecules is the hydrogen from the alcohol group. Consequently, the rest of the ester structure consists of the oxygen and whatever R group was present on the alcohol. This new functional group is what's called the ester functional group, E-S-T-E-R. Notice it's spelled differently than the woman's name. Esters are actually fairly interesting organic molecules for two reasons. The first reason is that they undergo many different chemical reactions, and we'll see some of them in a couple minutes. The other reason esters could be considered to be interesting is that they tend to have fairly easy to recognize aromas. And unlike thiols, which contain sulfur and had displeasing aromas, many esters have fragrant aromas that people do enjoy. So when you smell something like a pineapple or a pine tree or lavender, some of the compounds that you're smelling are esters. Esters are also responsible for some of the smells like cinnamon and pine trees and even the smell of beer. So while there are esters that have displeasing smells, many of them have fairly pleasing aromas to the human nose. Let's try an esterification example. Draw the ester that forms from the reaction between acetic acid and methanol in acidic conditions. Pause the video, draw out the structures of these two reactants, and see if you can draw the ester that results. To draw the structure of the ester, I'll start by drawing the structure of each product. Acetic acid contains two carbons as well as the carbonyl bond and OH group that makes it a carboxylic acid. This molecule is also referred to as ethanoic acid. It's then going to react with methanol, and to make it as easy as possible to see this reaction, I like to line up the OH groups right next to each other. For methanol, my OH group is connected to a carbon with 3 hydrogens. In the presence of acid, these two molecules will react to create a new ester. To figure out the structure of the ester, now I simply remove the OH group from the carboxylic acid and the hydrogen from the methanol. That means that one of the byproducts of this reaction will be a water molecule. And as we've said before, you're welcome to include that in the products, but it's usually not necessary. So after this reaction is complete, I'll still have the two carbons and the carbonyl bond from the acetic acid, but now it will be directly connected to what was essentially the methanol minus its hydrogen. This is the product of the reaction between acetic acid and methanol. And in the next couple minutes, we'll learn how to name it. Naming esters is actually fairly simple because it involves two parts, and both of the parts we've actually learned previously for other types of structures. The ester name is a two-part name that consists of essentially what was part of the alcohol that was used to produce it and what was originally part of the carboxylic acid. We treat the part of the molecule that was originally an alcohol as the substituent on an ester. So we'll be naming it using a YL ending, often with names like methyl, ethyl, propyl, and so on. The backbone of the ester name is the part that was originally part of the carboxylic acid. We'll change the carboxylic acid name so it's a carboxylate, because if you think about it, what we've really done is removed a hydrogen from the carboxylic acid. Let's look at the example we just did. When we reacted acetic acid with methanol, this is the structure that resulted. Let's name this molecule using these IUPAC rules. The substituent part of this ester is the part that was originally part of the alcohol. We know that that's the part connected to the oxygen, but not on the same side as the carbonyl. This molecule contains one carbon on the substituent branch, and we know one carbon is the methyl substituent. Notice that it was initially part of methanol, so we end up having methyl in part of this name. The backbone of an ester name comes from the part of the molecule that was part of the carboxylic acid. In this case, our carboxylic acid was acetic acid. However, the acetic acid has essentially lost its hydrogen, becoming a carboxylate. We know the carboxylate name for acetic acid is acetate if we're using common naming, or if I had called this by the IUPAC systematic standard name, which would be ethanoic acid, I could also call this ethanoate. So either one of these would be correct when we put them together. To get the final name for this molecule, I always put the substituent before the backbone, just as we did all the way back as far as in alkane names. So there's two correct answers for the name of this particular ester. One is to call it methyl acetate. The other is to call it methyl ethanoate. And again, it just depends on whether you prefer to use the common name or the more systematic name. Either one is completely acceptable, although I will tell you, you're far more likely to see it referred to as methyl acetate because acetate's a far more common term. Let's try another example. I'll do this molecule in a line structure form so we can see it written in a different way. Go ahead and name this ester. In order to name the ester, the first thing I need to do is decide which part of this molecule is the substituent and which part is the backbone. If you find the carbonyl carbon and find the oxygen that's single bonded to it, that's essentially where I should divide the molecule in half. Everything that's on the side opposite the carbonyl bond is part of my substituent. Everything on the same side as the carbonyl bond is going to be my carboxylate backbone. So now to name this molecule. My substituent in this case contains 3 carbons, so I'll call it the propyl substituent. If I needed to synthesize this molecule, I would have used propanol to do it. Now to name the backbone. There's a total of 1, 2, 3, 4 carbons here, so I can use either a systematic name or a common name. The systematic name for the carboxylate that contains 4 carbons is butanoate, so I could call this molecule propyl butanoate. If I wanted to use the common name for this particular carboxylate, I would think that 4 carbons is butyric acid, which means the carboxylate form would be butyrate. That means that I could also name this molecule propyl butyrate. Whether I call it propyl butanoate or propyl butyrate, that would be considered a correct name for this particular ester. Now the esterification reaction isn't limited to just very simple molecules. In fact, it can be used to make much longer and more complex molecules, including ester-type polymers. To do a polymer from an ester molecule, something has to be different about the structure than the examples we've just seen previously. And it's similar to what we learned when we did alkene polymers. If you recall alkene polymers, these were reactions where we had a carbon-carbon double bond and a reaction happened on both sides of the double bond, creating a long repeating chain. The same is true with esters, with a couple caveats. First, we can't just use one molecule for these reactions because esterification involves two. It involves a carboxylic acid and an alcohol. But to ensure that this reaction happens on both sides, we'll actually need a dicarboxylic acid and a diol, which is to say we need carboxylic acids to exist on both sides of the carboxylic acid molecule, and we need an alcohol group to actually exist on both sides of the alcohol. As a result of this, the esterification reaction happens on both ends of the molecule, and what you get is a polymer. Because it's a polymer that contains the ester functional group, we call it a polyester, a term you're probably familiar with. Let me show you an example of how this happens. The first required molecule, if esterification is going to be used to make a polyester, is a dicarboxylic acid. That means it's a molecule that contains a carboxylic acid on one side as well as another carboxylic acid group on the other side. In between these groups can be just about anything. They can actually be directly attached to each other. They might have a carbon in between them, or two carbons, or they might have a long chain or a more complex structure. So I'll write an R group here, and I'm writing it as R1 because we'll see in a second that there's another R group that'll also come into play. That other R group comes from the diol. In esterification, we react a carboxylic acid with an alcohol. Well, to form a polyester, we react a dicarboxylic acid with a diol, which means we're reacting an alcohol group on each side of a molecule. Those two alcohol groups can be connected through one carbon, two carbons, or a much larger or more complex structure. I'll just call it R2. So here is where the polyesterification reaction can happen. And it happens the same way as in the examples we've seen previously. Let's focus on just one part of this reaction, the part where the OH group is removed from the carboxylic acid and it bonds with the hydrogen from the alcohol. In that process, we'll create a new single bond and an ester functional group. But this reaction has to happen on both sides of the molecule, so I actually need to continue drawing these structures. For instance, I'll have to draw another dicarboxylic acid, the same one as I had in the first case. Then the reaction can happen again between the functional groups on each of these sides. And what you end up with is a regular repeating pattern. To draw this molecule, why don't I start with the R1 group? The R1 group is bonded to the carbonyl bond, and it was bonded directly to the OH, but this is where I now have a new bond that creates the ester functional group. Now I'm working with this oxygen here. That oxygen is bonded to whatever was in between the two alcohol groups, and in turn it has an oxygen on the other side. But what is this oxygen connected to? Well, here again we see that an esterification reaction happened. So now this oxygen is actually part of a new ester functional group. Now I'm dealing with this carbonyl bond here. It's connected to the R1 group, which in turn is connected to a carbonyl bond, and I can continue to repeat this process over and over. This carbonyl bond is in turn connected to an oxygen, and again it's really this oxygen here. So now I have whatever was in between the two alcohol groups, and the process continues. You can do this for pretty much as much space as you have on your page, but the important thing is make sure you stop at an appropriate point. Notice I just wrote R1. The first thing I wrote on this side is R1, and I want to make sure that I have a regular repeating pattern. So to make this correct, what I'll do is why don't I erase the R1 on this side, and I'm going to draw my brackets, just as we did with alkene polymers, through these bonds at the end. This ensures that if I was to repeat this, almost like a stamp that we stamped over and over and over again from one end to another, I would get the same regular repeating pattern. Now these are obviously more technical than the alkene polymers we've seen previously, But here's one thing you can do to make them a lot easier. Keep track of where your ester functional group is. The ester functional group consists of the carbonyl bond as well as a single bond to the oxygen, which goes on to another carbon. I should see that ester functional group repeating over and over, and it changes direction, so to speak. Notice that every time I find the ester functional group, it's almost like I'm writing an L, and the L is either pointing to the left or to the right. One of the most common mistakes that people make when drawing these structures is they accidentally omit the oxygen. For that reason, if you go through and locate each carbonyl bond and ensure that that carbon is also directly connected to exactly one oxygen, you'll be sure that you did the structure correctly. Notice also that the R groups alternate, R1, R2, R1, R2, and so on. This, again, is what we call a polyester. It's an example of an esterification reaction that's happened in a repeating manner. Let's try an example. Take a couple minutes and draw the polyester that results from the esterification reaction of these two molecules. One of the molecules, which I'm drawing now, is our dicarboxylic acid. And what the R group is in this dicarboxylic acid is actually a benzene ring. So it's a benzene ring with a carboxylic acid attached on each side. This is what's called terephthalic acid. Terephthalic acid is actually a very common ingredient that's used in polyesterification reactions. The diol, or dialcohol, that's used in this reaction is ethylene glycol. It's two carbons bonded together with an OH group on each side, as well as the additional hydrogen. So ethylene glycol reacts with terephthalic acid through an esterification polymer formation reaction in the presence of acid. Go ahead and draw a regular repeating pattern of what's produced during this reaction. For now, go ahead and draw as many of the regular repeating units, the monomers of this reaction, as possible, or as many will fit on your page, because it's really good practice. Pause the video and start it again when you're ready to check your answer. To draw the structure of the polyester that results from terephthalic acid and ethylene glycol, first I have to decide where to start. I tend to start usually at the first carbonyl bond. So let's put my bracket there, and I'll draw the carbonyl bond bonded to a benzene ring and then another carbonyl bond. Now I get to the first carbon-oxygen single bond. This is where the esterification reaction has happened and where a water molecule has essentially been removed. That means on the other side, I have to show what carbons were present in the alcohol. In this case, it was two CH2s, followed by the oxygen on the far side of the alcohol. Now I could stop right here, draw a bracket, and have a complete and correct answer for what the monomer, or the regular repeating unit, is for this polyester. But for practice, let's keep going. This oxygen is now connected to a carbonyl bond. And at this point, we're back to the carbonyl bond on the left side of the benzene ring in terephthalic acid. So I'll pick up by drawing my benzene ring, another carbonyl bond, and I'm back to a single bond to oxygen and the alcohol again. And I can repeat this process as many times as I want. If I want to stop at a correct point, I need to make sure that I stop at the point that's represented by that bracket. That bracket immediately precedes the carbonyl bond of terephthalic acid, which would be the next thing I would write right here. So I could put the bracket here and stop. This would be two monomers of the polyester that's formed from these two compounds. Again, I could also have drawn my bracket right here, and I would be correct. Now, the reason I chose this particular polyester for an example is it's one that you're familiar with. The product of the polyesterification reaction between terephthalic acid and ethylene glycol is polyethylene terephthalate, much more commonly referred to as PET. This is actually recyclable plastic number 1. And if you were to go home and flip over many of the plastic containers in your house, a great deal of them would actually be polyethylene terephthalate, or PET. So while it does have a more complex structure than a simple alkene polymer, it certainly still has widespread use in our day-to-day lives. This brings us to the last ester chemical reaction that I'd like you to learn, and it's what's called ester hydrolysis. We've seen hydrolysis before, most notably in the section on acetyl hydrolysis. And there we learned that hydrolysis means breaking something apart by chemically adding water. So in the case of ester hydrolysis, we'll break apart the ester molecule by chemically reacting it with H2O. Generally, this is a fairly straightforward reaction because we'll essentially get the initial organic components that would have been used to synthesize the ester. So it's a little bit like reversing the esterification reaction. However, it is important to notice that conditions matter. Most specifically, the pH conditions under which the reaction is done. When ester hydrolysis is performed under relatively acidic conditions, usually in the presence of an acid catalyst, what happens is we exactly reverse the esterification reaction. So knowing that an ester itself has a functional group structure like this means that if we react it with water in the presence of an acid catalyst or acidic conditions, we'll actually break this molecule in half and reform the initial carboxylic acid that was present as well as the initial alcohol that was present. I basically recreate my two organic molecules. For this reason, ester hydrolysis under acidic conditions is pretty straightforward. Basic conditions, however, are much more interesting. Here's why. Let's start by actually thinking about the hydrolysis the way we did for acidic conditions. We have an ester functional group, and we imagine that we're essentially going to use water to break apart the molecule. Where the molecule breaks is essentially where the carboxylic acid and alcohol would have initially come together to synthesize the ester in the first place. When this is done under basic conditions, one thing will change from acidic conditions, and where it changes is in our product. The thing that won't change is that we'll still reproduce the exact same alcohol that you would have used to synthesize the ester in the first place. So in that way, basic conditions are similar to acidic conditions. But here's what's different. If I was doing this under acidic conditions, I would write the structure for the carboxylic acid that must have been used to originally synthesize the molecule. But if a base is present, that base, let's say it's something like sodium hydroxide, is a chemical that will react with an acid, like carboxylic acid. So sure enough, what you have here is a secondary reaction. While ester hydrolysis might return an alcohol and a carboxylic acid to you as products, the base that's present will instantly react with that carboxylic acid, as we saw in the previous section when we studied carboxylic acid and base reactions. So the carboxylic acid in question will actually lose its hydrogen, and in its place it will develop a negative charge, and it will bond with whatever cation is present from that particular base. So notice that the products of this reaction are not a carboxylic acid and an alcohol as happened in acid conditions. Instead, we still get the alcohol, but instead we get a carboxylate salt. So we're really experiencing a slightly different reaction when we do this under basic conditions. The base-catalyzed ester hydrolysis reaction is often referred to as a saponification reaction. So we've basically learned a couple nicknames for chemical reactions in this section. We have esterification, which is the making of an ester. We have acid-catalyzed ester hydrolysis, and now we've also seen base-catalyzed ester hydrolysis, which can also be referred to as saponification. So why is it that base-catalyzed ester hydrolysis has this little nickname, saponification, but acid-catalyzed ester hydrolysis doesn't? Well, the reason has to do with the historical origins of the saponification reaction, or at least our understandings of it. Saponification is an incredibly old process. We actually have historical records of people purposely doing saponification reactions as far back as 2800 BCE. That's nearly 5,000 years ago. So why were people 5,000 years ago doing base catalyzed ester hydrolysis? Well, like so many things in science, this was basically a great discovery that people happened upon by accident. And the saponification itself wasn't done because these were ancient organic chemistry students, but rather because it was used to produce soap. Saponification gets its name from the Latin word sapo, which means soap, which was even previously derived from the term sebum, or fat. And that indicates where the reactants were coming from. As you can imagine, this type of ancient saponification wasn't done using reagents in a chemical laboratory. Rather, it was done with things that people had lying around. The first thing that you need to do a saponification reaction is the ester itself. Well, of course, people 5,000 years ago couldn't buy an ester from any organic supply company, but what they did have access to was fat. In fat, we find molecules called triglycerides, and triglycerides are actually molecules that contain 3 separate ester functional groups. Many times the fat came from animals that had been slaughtered for food. But there are also plenty of times where it came from vegetable sources. One of the most famous is coconut oil and coconut fat. So that's where the ester came from, was fat either from an animal or plant source. The other thing that you need to do a saponification reaction is water and the presence of a base catalyst. This came from what's called lye. Lye is essentially sodium hydroxide, but it's usually derived from not the neatest and cleanest sources. And in the case of historical saponification, it was usually achieved by mixing wood ash with water and heating it. As that happened, you had both the necessary reactant, water, as well as the sodium hydroxide-based catalyst needed to complete the reaction. So by mixing animal or plant fats and oils with this mixture of lye, essentially wood ash cooked in water, they were able to create a substance similar to what we think of as modern soap. So that's the historical perspective on saponification. But why does saponification create soap? I mean, yeah, this happened, but why is it any good at getting things clean? Well, the answer has to do with one of the products of saponification. We already said that it produces both an alcohol and a carboxylate salt. Well, a carboxylate salt is an example of what's called an amphiphilic molecule. It's a molecule that contains 2 parts. Notice the use here of the prefix amphi, which you probably recognize from words like amphibian. Amphiphilic means liking 2 or more things. And in the case of amphiphilic molecules, these are molecules that like, or mix well with, both polar and nonpolar substances. The carboxylate salt that is produced during saponification, especially in the case of the historical reaction with triglycerides, creates a molecule that has both a polar part and a nonpolar part. Now, in the modern era, most soaps are actually not carboxylate salts. Rather, they're sulfate salts, which is really similar. And in fact, next time you're taking a shower, if you turn over your shampoo or if your soap has a label, you might recognize a couple of these compounds. 2 of the most common soap-like compounds that are used in the modern era are sodium lauryl sulfate and sodium lauryl sulfate. Here's what they look like. Both sodium lauryl sulfate and sodium lauryl sulfate consist of a sulfate group on one end and a long carbon chain. The sulfate group is very similar to the carboxylate group. It contains an O- and therefore it's ionic. We know ionic substances mix well with water. The other end of the molecule contains a long carbon chain, which is very nonpolar. Therefore, that part of the molecule will mix very well with things like oil, grease, grime, dirt, and other things you might want to remove. So what an amphiphilic molecule does whether it's soap or used in another setting, is it allows us to mix together polar and nonpolar substances. In the case of both these sulfate salts as well as carboxylate salts, we have an ionic end to the molecule and an organic end, and that allows it to basically act as a matchmaker between oil molecules and water molecules. So that's how our modern soap works. But not to get too off subject, let's go back and do some practice questions with acid and base catalyzed hydrolysis of esters. Write the products that result from the following hydrolysis reactions. And to give you a little bit of extra practice, instead of giving you the ester structure for your starting reactant, I'm just going to give you its name. The name of the ester we'll start with is methylformate. So draw the structure of methylformate and then do the following reactions. Take methylformate and hydrolyze it in the presence of acid. That would be called acid-catalyzed ester hydrolysis. Then go ahead and take the methylformate and again hydrolyze it, but this time do it in the presence of a base. Let's use potassium hydroxide. That would be called base-catalyzed ester hydrolysis or saponification. Go ahead and give it a try. The structure of methylformate is actually the simplest ester you can possibly draw because it consists of a methyl group connected directly to the oxygen, and then the carbonyl group is actually just a one-carbon group. That means it contains a carbonyl bond with nothing else attached to it other than a hydrogen. This is the structure of methylformate because it comes from the terms methanol and formic acid. You could also call it methyl methanoate if you were using the standard IUPAC systematic terms. Now, if you haven't already, go ahead and do these two chemical reactions. In the acid-catalyzed hydrolysis of methylformate, we'll get the two initial products that would have been used to synthesize this ester. That means that the carboxylic acid consists of just one carbon, and that would be formic acid. Or again, it could also be called methanoic acid. The other product will be the initial alcohol, which in this case would be methanol. So the products of acid-catalyzed hydrolysis of methylformate are formic acid and methanol. Now for the base-catalyzed hydrolysis, better known as saponification, I will get the same methanol molecule because the alcohol is not affected by the presence of the base catalyst. But what's different is that I won't get formic acid. Formic acid, of course, is a carboxylic acid, so it will instantly react with the potassium hydroxide, the base. The result is my formic acid will deprotonate, and I'll be left with the salt. In other words, I'll write an O- and bond it with the K+, the potassium ion, from the potassium hydroxide. The name of this substance is potassium formate, because it's the ionic name for the carboxylate salt. And again, it could be called potassium methanoate if you were using the systematic naming. There's plenty more examples of these on our website if you'd like to do additional practice, but this completes the ester reactions that we'll be looking at in this section.